Few updates. Now, the plan for today is basically to work on this example. So what you have here is a cross-section with different wall thicknesses, a rectangular cross-section with different wall thicknesses. So what I propose to do here is do the analysis for the full effective cross-section, so without idealization. So get the shear flows like we did 2 or 3 weeks ago without idealizations. And then, after that, in the second half of the lecture today, I propose that we do the idealization of this section and do the shear flows for the idealized cross-section, okay? And then we can compare the solutions. All right? Let's start then the full effective analysis. So, just going to write here the equation. We talk about that. So the shear flow is going to be a function of this local variable. And this needs to be equal to an initial shear flow. I can call it Q0 minus. So I'm going to put here the simplified equation because from symmetry, right? This cross-section is symmetric. So we get the transverse shear force in the vertical direction divided by the second moment of area about this x-axis. I can put like this. And then we need to do the integral from 0 to this local variable s of the thickness of the wall times the distance to the neutral axis, right? Remember this equation? We did this already for the full effective cross-section. Okay? In fact, this equation is too big. Let me rewrite this equation a bit better. Okay, and let's now save this equation here. This is much better like this, right? Okay, we will need to use this equation many times. All right, so the first thing we have to do is the second moment of area, this Ixx. We need to calculate this. So I propose, if we do something like this, we need to divide this cross-section let's do like this. We will have this rectangle here in the top. This one in red, okay? Why is this not writing anymore? Okay, which is going to be equal to this one here in the bottom. Okay, and then in green I can say I will have this one here in green, and then in blue I can say I will have this one, which is going to be different from the other one because the thickness of this wall is different, right? So this one in blue. Okay? This, I can do this better now. So we have this. So let's start with the ones in red. So we have the centroid of this rectangle in red is here somewhere. So let's say this is x bar. I want to have the second moment of area about the x-axis produced by this rectangle in red, which I know is going to be equal to the second moment of area about the axis x bar plus the area of the rectangle times the square of the distance between the parallel axes. The parallel axes are these ones here. So the distance I need is this one. Right? Parallel axis is x bar and... Sorry, in fact, I'm using here x bar, but I have x bar here, right? So I think it's better if I do this way. So this is not x bar, this is x, okay? This is x, yes. It's easier this way. So this is the parallel axis theorem. We talk about this in year 1. We talked about this a couple of weeks ago. So if I continue, so this x bar is my bh power 3 over 12. Remember this equation for rectangles? So the width of the rectangle is this 200, right? So the width is 200. The height is 2 millimeters. 2 millimeters, so I need to multiply by 2 millimeters power 3. And I need to divide this by 12. So this is my x bar. I need to add the area of the rectangle, which is 200 times 2. And I need to multiply the area now by the square of the distance. The distance is 49 square, right? Distance square. Okay? Can you please do this for me and let me know how much?
9.61 times 10 pounds.
Yeah, that's great. But look, the rectangle here in the bottom, this one in red here in the bottom, I think I can just multiply this by 2. You agree?
Yes.
I can multiply this by 2 because, look, this x bar is going to be the same. The area of the rectangle in the bottom is the same as the area of the rectangle in the top. The distance between the parallel axes is the same. So I can just multiply this by 2. And can you please multiply that result by 2?
4.92 times 10 to the 6.
Millimeters power 4, right? So I'm going to add this one here, 1.92 times 10 6. You know this is the contribution from these two rectangles in red. Okay? Now, switching to green, I want the second moment of area produced by this rectangle in green color in my figure about this axis x. Here, I just need to use this bh power 3 over 12, right? So I just need to use this equation. The width is how much? Is 3? The
96.
height is 96. So power 3 over 12. How much is this?
2.21 times 10 to the 5.
10 to the
5.
5. This looks like minus 5. 5. Okay, I can add this one here. Let me just delete this to find some space. I can just add this 2.21 10 to the 5. And I can now do the contribution from the rectangle in blue. which is, again, same equation, b h power 3 over 12. In our case, our width is 1. The height is 96 as well, right? You agree? Oh, how much is this?
7.37 times 10 to the 4.
And I can just add this result here. 7.37 times 10 to the 4. Right? And now if I add all of this together, I will have the total second moment of area. Can you please tell me how much that is?
2.21 times 10 to the 6.
2.21 times 10 to the 6. Okay? Very good. You all understand this? This is quite easy, right? So I can replace here. What about that? 2.21 times 10 to the 6. Let me just replace here 2.21 times 10 to the 6. Okay? There's one more thing I can replace, which is the transverse shear force, this 100 kilonewtons. I can convert this to newtons and replace this SY. I'm going to do that. Then we got minus 10 to the 5, right? It's correct, right? Okay? Well done. Can I delete this second moment of area? Is clear for you? So I'm going to delete all of this, including these colors here. And this. Okay. In fact, this minus with minus here, I can replace this minus and minus with a plus, right? What do you think? I can just put here a plus. Try to make it simple. So this is the equation we are going to do. Now we just need to start our integration. We need to choose a point to start. It can be point A, point B, point C, or point D. Which one do you want? A. Okay? So, choosing point A, we will start our analysis here from point A. So we will define a local variable starting at point A. I suggest you put like this, SA. So you know you are starting, the point A means SA equal to 0. Point B means this coordinate SA equal to 2000 millimeters, okay? That's how this local variable works.
Sorry.
Yeah.
Does the SA start in the middle of the 3 millimeters width? Does it start in the center or does it start on the
Oh yeah. We of course. I'm not always the correct,
Is it in the middle?
but usually it's in the center line. So this SA starts here in the center line of the cross section. Okay. So let's say point B is going to be. So you have 200. You remove 1. So 199. Sorry, 1 point off 198.5, and you remove off 198. That is more accurate. The difference at the end is not going to be much, to be honest. But yeah, that is the most accurate. Okay. All right. So using this equation here, I will say then that the shear flow as a function of this local variable SA, right? Because I'm going to do the analysis of my shear flow from point A, from this point A to point B, in this part of my cross section, okay? So the shear flow will be a function of this local variable SA, okay? That's what this means here. And I know that from this equation that this needs to be equal. This is an initial shear flow. When it is a free edge, we know that initial shear flow is 0, but this is not a free edge. So I'm going to say my initial shear flow at point A, I'm going to say it is equal to QA. It's unknown. Like we did this already. 2 weeks ago or 3 weeks ago. Now, this term here, I can simplify a little bit more. This is going to be 1 over 2, 22.1. You agree with me? It's correct, right? And now I need to do the integral. And this integral starts on, so this integral is going to be on the local variable SA, okay? And the limits for this integral, so the starting is when SA is equal to 0, we are at point A. So the lower limit is going to be SA equal to 0, right? Then we are at point A. And then I'm going to say the upper limit of the integral is going to be a generic variable, SA, because it's only this way I can get the function for my shear flow. Okay? If I replace here SA by 198 millimeters, I will get the total shear flow, right? Which is something that I'm not looking for. I'm looking how the shear flow flows in that wall, right? And then I need to include now the thickness of the wall. The thickness is 2 millimeters, is constant. I'm just going to delete this because I need more space. And then this y, don't forget what this y is the distance to neutral axis. Which distance is this? Imagine you are at this SA equal, you are in this point. You need this distance to neutral axis. This is the y that you need. Imagine you are at this point. This is the y that you need. You are at this point. This is the y coordinate that you need, and so on. Any point given by this coordinate SA will have a distance to the neutral axis which is equal to 49 and is constant, right? So I can say that this distance y here inside this integral is going to be always equal to 49 to this wall. And in fact, this is the simplest integral you can do, because this integral of a constant is very easy to do, right? The primitive of this. So we can simplify this a little bit and say that I can send this 2 times 49 outside of the integral, and then that will make 98, right? And then I just need to multiply this by SA, right? Which is the primitive of 1 is equal to the upper limit minus the lower limit, which in this case is 0. So, and then as you can see here from this equation, we got a linear distribution for shear flow. Basically, we got something like this. Assuming, for example, this is QA, we don't know how much is QA, right? But assuming this is QA, we got the shear flow. This is the equation of a line, right? And this is the slope of that line, which is positive, which means that we will get the shear flow increasing from point A to point B, and this is going to be my shear flow at point B, right? And this is how the shear will distribute in this wall at the top, okay? This is how the shear evolves from point A to point B in a linear manner, right? You can see from this equation, it evolves in a linear manner with this local coordinate SA. Okay, this is a kind of a revision of what we did already. We did a similar example with this. And then, of course, we can calculate this QB. How do I get the value of this QB? I'm going to move this a little bit here. because I want not to do something like this. QB is going to be equal to what? What do I have to do to get the shear flow that is arriving at this point B? Look at this equation here. What do I have to do to this equation to get the shear flow arriving at point B?
SA is equal to 198.
Exactly. I need to replace SA by 198, and then I will get the shear flow arriving at point B. Okay? So if you do that, you will get QB is going to be equal to QA plus 98 over 22.1 times 198 millimeters, like you said. And then if you do this, can you give me a final number for this? 98 times 198 over 22.1?
878.
878. 878, like this, right? Okay? So this is the shear flow we obtained at point B by just replacing SA in this equation by 198 millimeters. Why do we need this QB? Because I need to continue my analysis now from point B to point C. And I will do that in... so I'm going to copy this. Copy. Paste. Okay? So I will have now what? I will have this is also going to be equal to my QB, is the same, is equal to QA plus 878. And now I want to see how the shear flows from point B to point C. In fact, I can move this here and zoom this a little bit more, like this. Now I can say something like this. I will have a local variable starting at point B. I will say this local variable is my SB. SB equal to 0. It means we are at point B. SB equal to 98 millimeters. We are at point C. Okay? And then I can say the shear flow QSB, then I know is the shear flow in this wall from point B to point C, is going to be equal to the shear flow, initial shear flow, which is when SB is equal to 0. And that initial shear flow is going to be equal to QB, right? Plus 1 over 22.1. Now integral from 0 to SB. Thickness of the wall, which is 1 millimeter, times the distance to neutral axis. Now here, for the distance to neutral axis, we need to find an equation. For example, I'm going to use the green color. Imagine your SB is equal to this. You are in this cross section, so this is your SB. Okay? In this case, you need the distance of this cross section to neutral axis is given by this. This is the y that you need in your equation, okay? So how do you get your y from this? If you look at this, you know this total distance, right, from here to here, which is 49 millimeters. So if you look at this, you can say that your distance to neutral axis is equal to what? 49 minus SB, exactly. Right? Everybody got this? It works. Then you can use 2 points to check. One is when SB is equal to 0. For SB equal to 0, you are at point B, right? So the distance y to neutral axis in that case should be equal to 49, which is correct, right? You can use other point, this point here in the neutral axis. This point in the neutral axis is when SB is equal to 49. If you replace here SB by 49, you got 49 minus 49 means the distance to the neutral axis is 0, which is correct, right? For this point. The distance of this point here to the neutral axis is 0, right? That point is at the neutral axis. Okay, so this is the equation you need to use. There's no doubt. And then I will just replace this equation here. So 49 minus SB. And then I just need to integrate this along this SB local direction. Okay? So if I do that very quickly, oh, there's one more thing I should do. I should replace this QB by QA plus 878. So if I do all of that, I will get right? And now I can say I will have here 49 times SB minus SB squared over 2. I'm just getting the primitive, right, of that integral, right? I think it's correct, right? You agree? And so, look at this equation now. We will have an equation that gives me the distribution of the shear flow when it comes from point B to point C, and that distribution is quadratic. Okay? That this, you see, you have this square SB square, so you have a quadratic function in SB, so it means you will get something like this for your distribution of the shear flow, a quadratic one. Okay? And then your shear flow will change in this manner. And we can calculate the shear flow that is arriving at point C, QC, by doing what? How much is this shear flow arriving at point C? What do I have to do? I need to... It's same as... Okay, but I just replace SB by 98, and then I should get this QC. Okay? Okay, if you do that, look at this. If I replace SB by 98, I will get inside these square brackets, I will have 49 times 98 minus, I'm going to write like this, 98 times 98, which is 98 squared over 2. This is equal to 49 times 98 minus 98 over 2 is 49 times 98. This is cancel each other, right? And then at the end you get the shear flow equal to QA plus 878, which means the shear flow equal to, at point C, is equal to the shear flow arriving at point B, right? So we can say that this QC is going to be equal to QA plus 878. Same as this one, right? Same. Right? Which makes sense from symmetry. Makes sense from symmetry. Okay? Now we can continue, but I think from symmetry you can guess what is happening, right? So let me just copy this and put in a different page. I think you can imagine that, okay, we will have here QC, right? It's the same QC, this one. I can move it a little bit like this more. And then you can imagine, but you can do the calculations at home if you want. From symmetry, we are going to have here QA, right? And of course, this here below, we are going to have also a linear distribution for the shear flow. So we will have something like this. Okay? And in this wall, we will have this QA here at point A, same at point D, and then we'll have a quadratic distribution as well. So we will have something like this. At the end, you will have something like this. So these two bits I did it very quickly because I just used the symmetry of the cross-section. But you can, if you want at home, it's a good way to study. You can use this same equation to obtain the distribution of the shear flow on the wall CD and on the wall DA as well. Okay, so this is the distribution of the shear flow in the original or real cross section. What I propose to do before we do the break is just let's now evaluate how much are going to be the forces in the walls, total force in the walls, okay? And for that, I'm going to copy this whole thing. And I'm going to copy this equation here. And I'm going to copy the other equation for the quadratic distribution, which is this one. We need to keep these two equations. Okay? All right. So, what I propose now is, let's calculate first the force so I'm going to copy again this because I'm struggling with space here. I need to find. So let's use this equation. Oops. And let's focus on the wall in the top. So let me delete this one. Let's only focus on this wall. Oh, by the way, sorry, before we calculate the forces, we didn't calculate QA, right? This is incomplete. Yeah. Because we have this distribution, but we don't know how much is this QA. Ooh. We don't know how much is this QA. So we need to do this first. Okay, I'm sorry. So how do I get this QA? Sorry? Equation for the moments, right? So in order to do the equation for the moments, I need to have the total forces in the walls. Then I just multiply that total force by the distance to get the moment, right? So that's what I was trying to do here. So let's focus on that wall. The equation I need is this one. I will copy, paste. So this is the equation that I need. I can delete this guy here as well. Okay. So this is the equation that gives me the distribution of the shear flow in wall AB. So in order to get the force in wall AB, I need to do the integral again from SA equal to 0 and SA equal to 198. Then now I'm going to replace the upper limit of the integral with 198 because I want the total force in that wall. And I need to do the integral of the shear flow of this QSA. That's what we do to obtain the force. We do the integral of the shear flow in that wall. Okay? Basically what we are doing is, by doing the integral, we are adding all the shear flows at every single point of the wall. Adding all of them together, that corresponds doing the integral. Okay? So if I do that, I get the force. So I can just replace the shear flow QSA by that equation over there. Right? And then I just need to do the integral which is not difficult. So this means this force FAB is going to be equal to 198 QA plus 98 over 22.1 times 198 square over 2. Okay? So we will get something a little bit more simple than this. We will get 198 QA plus, can you tell me this number here, how much it is, please?
8.69 times 10 to the
4, okay? So we need to keep this result because we will have to use it. Okay? So this is the total force in my wall AB, still a function of QA because we still don't know how much is QA. So what I propose us to do is to evaluate the moments about this point D. Evaluate the moments about this point D. So I don't need to get the force in this wall. No, I don't need, because the moment is 0 about D. Same thing for the force in this wall. I don't need, because the moment about point D is going to be 0 as well, right? So the only one I need to have is on the wall AB, that we did already, is here. The equation is this. And I need to do it for wall BC as well. So in wall BC, I need to do, so I'm going to copy this in a new one. Copy, paste, don't forget we got this quadratic distribution, and the equation for this one is here, is this one here. I can copy again. Okay? And then, same thing, for the force in this wall, I need to, so the force in wall BC is going to be the integral for SB equal from 0 to 98, right? Of the shear flow, which is all of this. Right? I just need to integrate this one more time, then I get the force FBC. Okay? And then, if I do that, I will get 98 QA plus 878 times 98 plus 49 over 22.1 times 98 square over 2 minus 1 over 44.2 times 98 power 3 over 3. Right? So this will give me the force in wall BC equal to, I can say 98 QA plus, if you do all these maths for me, please, you give me a final number. So 1.6 times 10 to... 9.16, okay. Okay, so let's keep this one as well. All right, so we are almost there. And now finally I can say that yeah, the video is going to be available. You don't need to copy. So I will. What I'll do, we are finishing. I can feel you are stressing a bit. I'm stressing much more, trust me. But we are finishing. That is good news. This first half. So let me just copy this equation now to have the equations there. So I can copy this one. This is in wall AB. So we can say we will have something like this. In wall AB, this total force is going to be equal to this. Okay? This is my force in wall AB. Now, my force in wall BC, this force here, I'm going to copy this equation here. Yep. Is equal to this, all right? And now I can say, I'm going to use the blue color now, the summation of moments about point D produced by the internal shear flows, they need to be equal to the summation of moments produced by the external forces, which in this case about point D is equal to 0, right? So this means this FAB so this is my FAB is the force. So this is my FAB. I need to multiply this force by the 98 millimeters, which is the distance to get the moment. So I multiply this by 98. Plus, now I need to account for the moment produced by this force. So this force is this one here. I can just copy. Copy. So I'm going to continue here below. So this is my FBC. And I need to multiply this by 198 millimeters to get the moment. and this should be equal to 0 to be in equilibrium. Okay? So from this equation here, the only unknown that you have is QA. Can you please tell me how much is QA? So QA is going to be equal to, okay, this is the equation for QA. So the idea of lecture today is to solve this example in two different ways. One is the real, full, effective cross-section like this, which, as you can see, is a lot of work, right? And the idea is, on the second half now, after the break, we are going to do the idealization of this cross-section and do the shear flow in the idealized cross-section. Then you will see it's much easier. The results, that we are going to see the differences between the two and compare a bit the results we obtain, okay? All right? So how much is QA?
Oh, yes, negative number, right? Because it would be another way. I get minus 4.67 times 10 to the 6.
Minus 4.6
6, 7
times 10.
to the 6.
This is Newton per millimeter. This is a shear flow, right? Okay? So this means okay, so can you please now, let's do one test, very quick test. Let's just replace here your QA in this equation. Can you please do that? Can you replace your QA, which is 4.67 times 10 to the 6, or is minus, right? So don't forget to put minus signal there. And tell me how much is the force FBC. Okay, can you do that for me? So what I'm saying is that if you replace here, you will get 98 minus 98 times 4.67 times 10 to the 6 plus 9.16 times 10 to the 8. So this is going to be my FBC. This is equal to how much?
4.58 times 10 to the 8.
4.58 times 10
To the 8.
to the 8. To the 8. Something is not correct.
The answer's wrong.
Which answer is wrong?
That's my last one.
QAB.
FBC.
Yeah.
If you go back to that, it should be.
Which one is wrong? FBC?
Yeah, that one's supposed to be.
This number here. 91.6.
Yeah, that should be. 8.
Oh, God.
Yeah.
Okay, so give me the right one. So you are saying this one is wrong.
Yeah, it should be 8.96 times
8.96 times 10 to the 4.
That's
Yeah. Okay. All right. And the other one, FAB, is correct?
That should be.
That should be okay. Okay. So let me delete all of this. Let's see if I can do a very quick fix. If not, I will have to do during my sleep tonight again. So let me see. This one here is not correct, right? Can you repeat it again for me, please? What is this? Can you repeat that number again?
8.96.
Okay. So you need to replace here again. This one here is 8.96 times 10 to the 4. Okay, and then you will get a new QA. Please, can you calculate the new QA for me? So can you calculate the new QA again for me, please? We are almost there, hopefully. Okay, how much? You have it? You have this, huh? You have these powerful calculators now called iPhones or Androids or whatever. What's the problem with this? Looks not difficult to me. QA, please. The first one with answer will get a free coffee. Not from me, but... Not difficult, right?
I'll get minus 6.77 times 10 to the 2.
6.8 times 10 to the 2?
Yeah.
Everybody got this? Okay. Now please replace it here so that you will get 98 times 6.8 times 10 to the 2 plus 8.96 times 10 to the 4. How much is this equal to? This is going to be our force in wall BC.
2.3 times 10 to the 4.
2.3.
Yeah, it's mine, yes. Yeah, 2. Well, I got 2. Yeah, 2.3 times 10 to the 4.
Not good news. Are you sure about that? I suspect I will have to review this during my sleep tonight. We should get here something like 50 kilonewtons.
23.
Oh, maybe no. Maybe it's okay. Okay, tell me, please. I just found one thing. Tell me, please. Yeah.
In kilonewtons, 23 grams.
23.
Yeah, times 10 to the 3.
10 to the 3. So we got 23 kilonewtons. This is in wall BC. There is one situation here. Please just pay attention. I just realized now that the wall AD is different from the wall BC. So this means what? This means this distribution I put here, this is wrong. We need to do this one. This is correct in wall CD because it's symmetric from the wall in the top. But this one is wrong. So the shear flow in this wall, so you can do this at home. For the shear flow in this wall, you need to use that same equation. I'm going to write it here. You need to have a local variable starting here at point D, SD. This is still QA. The initial shear flow here at point D is QA. That is correct. And then you can say the shear flow flowing from point D to point A is going to be equal to the initial one, which is QA, plus this integral here. Let me just make sure. Yeah. 1 over 22.1 times the integral from 0 to SD. The thickness, which is 3 millimeters now, this is the difference, okay? Times the equation you will get is going to be minus 49 plus SD. You need to integrate this, okay? So it means you will get a shear flow which is going to be different from the shear flow in this wall. Why the pen is not writing anymore? Yeah. And then at the end, if you calculate the force, you should get a force in that wall of 27. Anyway, you can finalize this, not 27, 73, which is 100 minus these 23 kilonewtons we obtained here, okay? Anyway, this is something you can finalize at home. What I propose is now we will take this example and we will, in the second half, do the idealized cross-section, okay? And compare solutions, all right? So let's do that in the second half. Okay, let's continue then. It's a bit late. So, same cross-section. Let's do the idealization of this. So we need to calculate the area of the booms. I propose if we do something like this. So I propose if we do something like this for the idealized structure, 4 booms at point A, B, C, and D. And then we need to, so this is point A, B, C, and D. Of course, we will have the same 100 kilonewtons here. Okay? The neutral axis is going to be in the same place here. So the first thing we need to do to get the idealized structure is to get the area of these booms. And the equation we need to use to calculate the area is this one. The area of the boom is going to be equal to the width times the thickness over 6, multiplying 2 times the... So if I want to calculate the area, for example, if I have a panel like this, if this is boom 1, boom 2, if I want to calculate the area of boom 1, I need to have the ratio between the stresses, sigma 2 over sigma 1. Okay? And we saw that this stresses, sigma 1 and sigma 2, they come from the bending. And then if we replace these stresses from bending, we can conclude that we can replace this by the distance to neutral axis of boom 2 over the distance to neutral axis of boom 1. And this is the equation I'm going to use to get the area of the booms. Sorry? Yeah, don't forget this is only for a skin panel with 2 booms at the ends, right? But in this case, for example, if you look at, for example, let's say boom D, for example, if you look at this boom D is sharing a skin panel with boom A, but is also sharing a skin panel with boom C, right? So we need to have these 2 contributions. So what I mean is, for example, we can start with the area for boom D. Let's look first at this skin panel here. Okay? So I need, if I use this equation, I need the width of this panel, which is going to be equal to 98 millimeters. The thickness is the thickness of the wall, which is 3 millimeters, right? Over 6. I need to multiply this by 2 times. Now I need the ratio between the location of boom A, or the distance of boom A to the neutral axis, which is 49, right? And I need now to divide this by the distance of boom D to neutral axis, which is minus 49. And this is the contribution only from this panel here. Okay? I need to add now the contribution from this panel here that I am circling with red color. So I need to add now the contribution. So I need to add. The width of this panel is 198. The thickness is 2 millimeters. And then I need to multiply this again by 2, plus I need the ratio between the distance to neutral axis of boom C, which is minus 49, over the distance to neutral axis of boom D, which is minus 49. Okay? And then I will get the area of my boom D. I can continue here. So we will get 98 over 2, which is 49, times 2 minus 1, so 49 times 1. And then I will get here 198 over 3. How much is that? Okay, it doesn't matter. 198 over 3 times 3. Or that is very easy. I will get 49 plus 198, which is equal to 247 square millimeters. This is the area of my boom D. Okay? You see how I obtained the area of boom D? What if I do now boom A, the area for boom A? What do you think? I need to consider this wall here, which is equal to this wall when we were looking for boom D, right? And I need to consider this wall here, which is the same as, so what do you think? The same area, right? So I can say this is going to be equal also to the area of my boom A. That is done. Okay? 247 square millimeters is this one, okay? 247 square millimeters is the area of boom A and the area of boom D. And now I can calculate the area of boom B. It will be equal to the area of boom C, yes, you're right. But we need to calculate at least this one, right? So the area, let's do the area of boom B. So I need to look at this panel. So the width is 198. The thickness is 2 millimeters over 6. 2 plus the ratio between boom A, the distance to neutral axis, which is 49, over the distance to neutral axis of boom B, which is also 49. And now I need to look at this panel here. So I need to add the contribution of this panel, because boom B is also sharing with this panel. And the width is 98. The thickness now is 1 millimeter over 6. So 2 plus. Distance to the neutral axis of boom C, which is minus 49, over the distance to the neutral axis of boom B, which is plus 49. All right? Are you following this? And then if you simplify, you can say that the area of boom C is going to be equal to the area of boom B, and equal to, so this is, we get here 2 plus 1 is 3. 3 over 6 is going to be equal to 1 over 2. The 2 cancel with 2, so we got 198. And here we'll get minus 1. So 98 over 6, how much is that? How much is 98 dividing by 6? So how much is this? You can just tell me the total area at the end.
16.3 recurring.
16 point?
3.
No,
Needs to be more.
That's for 98 over 6. That's the 98 over 6. The whole area is 214.
Okay. Add
214.3 recurring.
214.3 millimeters square. So this area should be lower than the area of boom D. Yes, it is lower because this wall here has thickness which is less than this thickness, so it makes sense it to be lower than that, okay? All right, so do you see how we can very easily get the idealized structure? So now we will have something like this. We will have our cross-section idealized, something like this. The area, so this is A, B, C, D. The area of boom A is equal to the area of boom D equal to 247. The area of boom B equal to the area of boom C equal to 214.3, right? Okay? So we have this. Of course, we have here now the 100 kilonewtons. We can just now do our analysis for the idealized structure. So our neutral axis is here. X. So we need to, the formula we need is this one. The shear flow after crossing the boom is equal to the shear flow before crossing the boom minus times the area of the boom times the distance to neutral axis. So this is the equation for the idealized structure. No integrals here. So we need to calculate the second moment of area, which for an idealized structure is just the summation in the number of booms. In this case, we have 4 booms of the area of each boom times the square of the distance to neutral axis of each boom, right? So we will have boom A and boom D, they have the same area, so I can multiply by 2. The area is 247. The distance to neutral axis is 49, which I need to square. This should give me the contribution from boom A and D, but I also have boom B and C. The area is 214.3. And the distance to neutral axis is also 49 square. So how much is this, please? Can you give me a final number for the second moment of area?
2.22 times 10 to the 6.
2.22 times 10 to the 6 millimeters per 4. Let's check with the previous one we obtained for the full effective cross-section. I don't remember. Oh, it's here. Very good. We are getting, so same result, look at this. Same result for the second moment of area for the idealized cross-section and the real cross-section, which is great. Let me just copy all of this. I don't need to copy, I can just... Okay, I will just replace here in this equation the second moment of area with 2.22, right? 2.2 times 10 to the 6. I can also replace this one here, minus 10 to the 5. Okay? And then I can also, this minus with minus will be a plus at the end. Okay, this is what I need. Now I can just copy this to a new one. And maybe copy this equation as well. And let's start now crossing the booms. Here we do a little bit different, right? We have to cross the booms, right? Remember, idealized structures. So we can say, for example, we need to get an initial orientation for the shear flow. So let's say this is my Q1, Q0, Q2, Q3, initial orientation for the shear flows, and now we cross the booms. So let's say crossing boom A. What we get is shear flow after crossing the boom A, which is Q1, needs to be equal to the shear flow before crossing the boom, which is Q0, plus, this is going to be 1 over 22, times the area of the boom that is being crossed, which is boom A, and the area is 247, times the distance of that boom to the neutral axis, which is 49. So this should give me Q1 equal to Q0 plus, can you give me a final number here?
550.
550. So this is going to be my Q1. We are going to save this result. Okay? Now, it's difficult to compare this with the previous one for the full effective because, as you can see, the shear flow Q1 between boom A and B in that wall is constant, right? It's not changing. While before, we obtained a linear distribution. So the shear flows we cannot compare directly between idealized configuration and the real configuration, okay? But they need to give at the end, they will be equal in an average sense, or they will give at the end the same equivalent force in the wall. What we have to do now, we have to cross boom B. Let me just copy this. Crossing boom B now. Shear flow after is Q2. Shear flow before is Q1, but Q1 is Q0 plus 550. I'm going just to replace here. Plus 1 over 22 times the area of boom B, which is 214.3, times the distance to the neutral axis, which is 49. Can you please tell me this is going to be equal to Q0 plus
1027.
1027?
Is it plus or minus?
It's plus, because we are always using this equation, right? And you get the plus in this equation there. We are always using this equation when we cross the booms, okay? So is 1027 is correct? So this is our Q2. Let's keep this result. Let's cross now boom C. We will get Q3 equal to Q1. Right? From symmetry. And let's cross boom D now. So I'm going to cross boom D. Crossing boom D. We obtain the shear flow after crossing, which is Q0, equal to the shear flow before crossing, which is Q3, which is equal to Q1, Okay, I'm going to do, I think it's better to do like this. The area of boom D is 247. Distance to neutral axis is minus 49. Careful with the signal now. We don't have the square of the distance, so the signal now is important. But we know that Q3 is going to be equal to Q1, and Q1 is equal to Q0 plus 550. So I'm going to replace in fact, I don't need to do this. I don't need to do this at all. Because, yeah, it's a waste of time what I'm doing, because instead of crossing boom D, I can just go directly now for the moment equation, right? To get Q0. You agree with me? Right? So what I'm saying is that I can calculate summation of moments about boom D for the shear flows, which is equal to, do you remember? I need to use this equation for the moments produced by the shear flow is 2 times the area times the shear flow in the wall. I told you this equation last week. The area is the area of this area connecting the boom where you are evaluating the moment, which in this case is boom D, and do 2 booms A and B for the wall AB, right? So if I connect these 3 booms, I get the area of this triangle, which is, so it's 2 times the area, which is, I need dimensions. Oh, sorry. 98, this is 98, this is 198, right? So the area is going to be 198 times 98 over 2, and the shear flow is Q1, which is equal to Q0 plus 550, right? So this is contribution for the moment, contribution from this shear flow Q1. I need to have now the contribution from shear flow Q2, this one, in this wall, and the area I need to use is this area here in green. Which is going to be the same area, right? So I need to add this contribution. And the shear flow is Q2, which we have here somewhere. Yes, Q0 plus 1027, right? Okay? And this needs to be equal to the moments produced by, so I'm going to put here, this needs to be equal to the summation of moments produced by the external forces in the same point D, which in this case, that moment produced by these 100 kilonewtons is 0, right? About point D. So this needs to be equal to 0. So this 2 cancels with this 2. This 2 cancels with this 2. We will have here, if I continue the equations here, we will have 2 times 198 times 98 times Q0 is going to be equal to minus 198 times 98 times 550 plus 1027, right? This gives, oh, this is very nice. This cancel, this cancel. I hope I'm not having any mistake here. Let me check again. So this is okay. Q0 is fine. Then we will have, seems okay to me, right? And then it means Q0 is going to be equal to minus 1,577 over 2, which is 788.5 newtons per millimeters. Okay? All right? Yeah. Very good. And now we can do a very quick check. We can do a check on the. Let me copy this one here. It's better. Let's do a check on the forces in the horizontal direction. That is very easy to understand because we have. Why is this rotating? Okay. We have Q3 equal to Q1. So this shear flow will cancel with this one. We have summation of forces in the horizontal direction equal to 0. That is very quick. Now for the vertical direction, we need to get the force in this wall, which is equal to, we got Q0 equal to 78.5 negative. So it means we will have a shear flow in this wall, which is going to be opposite in this direction and equal to 788.5. Okay? So in order to get the force in this wall, I need to multiply this 788.5 with the length. Don't forget, shear flow is a force per unit length. So I need to multiply by the length of this wall, which is 198. But I also have the contribution from this wall here now for the vertical forces. And I need to have Q2, but Q2 is equal to Q0 plus 1027. I'm going to write here. But Q0 is minus 788.5, so it means I will have a positive value for Q2 equal to, how much is 1027 minus 788.5? 238.5. So I need to add now here the contribution of the shear flow in wall BC, which is 238.5 times the length of the wall, which is 198. And hopefully today... Sorry?
The length for those will be numbers, yeah?
Oh, yeah, right. Yeah, same in the first one. The length of the wall is wrong. Is 98. Sorry. I just want to see if you are awake. Okay, how much is this?
1 times 10 to the 5.
How much?
1 times 10 to
1 times 10 to
the 5.
5, or if you want, 100 kilonewtons, which completely matches the external force we have there, okay? So this check is always good to do to make sure you have everything right at the end. All right? So, as you can see, the solution of the shear flows using idealized cross-section is much quicker, right? Much quicker than the real structure.
Would you let us choose an example?
Just one more thing. Wait. I will answer that question. Just one more thing. One more difference between the real structure and the idealized structure is the shear flows for the idealized structure, they are constant in the wall. For the real structure, they are not constant, right? You can clearly see that they have this kind of linear, quadratic variation. So they are more accurate in the real structure. Much more accurate, but the time you need to do these calculations is much more. And in the design, for example, in a wing, okay? When you don't know yet the configuration of your wing, you need to do a lot of stress analysis there. So we always start. So this design process is an iterative process. We do many iterations until we get the final wing, right? In the first iterations of the design process, we use the idealized structure a lot because we can have very quick calculations. We can decide, okay, I need to put one more spar here, one more stringer here and there, right? So we need to do very quick calculations at the beginning. And once we are confident about the final shape of the wing, then we can do the real structure calculation to get more accurate values, okay? You asked me something about the exam.
If you gave us something like this, would you just let us choose if we do which way we do it?
It's never a good idea to let you choose what to do in the exam. I will tell you. Do idealization or using the real structure, do the calculate shear flows, or using the idealized structure, calculate shear flows using the structural idealization, something like that, okay? Which one? Idealized, okay. The final one? This one? This? I cannot zoom out more than this. It doesn't allow me. What do you want to see? Is the final equation? Is this initial equation here, right? So this is, I try to put the red and green color, right? So the red is the contribution from this shear flow. The green is the contribution from this shear flow to the moment about point D, okay?
You go down to 2 times 198 times 9.
Yeah. One is from this bit here, but you also have the same one here, right? That's why I multiply by 2. Okay? All right. See you next week then.